Today I get to introduce you to my shortcut. For a while here, I've been able to figure sine, cosine, tangent, cotangent, secant, cosecant of different special angles and done it all in my head. I don't even need to look at the triangles. And statistically speaking, you're not all going to understand this, okay? So you don't have to do this, okay? What I'm giving you is an option. Does that make sense? This is an option where if your brain can wrap around this, man, you're going to be super fast. If your brain doesn't wrap around this, we're going to look at it multiple times off and on. You'll have opportunities to try to grasp it, but if you're just like, I just don't get it at all, triangles. You're stuck drawing them, which is a bummer, but you know, they work, right? As long as you're careful to make sure the hypotenuse is 2 and the long leg is the square root of 3, and as long as you're careful to, make sure you draw the 0, 90, 90 triangle correctly, and things like that. It works. Okay, so in your notes, I want you to write this down, the unit circle. The unit circle with line diagrams. The unit circle with line diagrams. Now, I will say this as well. When my teacher first taught it to me, I did not immediately wrap my brain around it. It was after the second or third time he kind of showed it that my brain clicked. Okay, so I would suggest don't dismiss this immediately because it was a game changer. Man, it sped up my work so much. So bear with me here. First of all, with a unit circle, the reason we call it a unit circle is that the radius is exactly equal to 1 unit. Okay, the radius is equal to exactly 1 unit. That's an important thing to keep in mind. So the way the unit circle works is we have a circle. The radius is 1. I'm going to draw the Cartesian plane within the circle. And we understand, of course, that this radius is 1, this radius is 1, this radius is 1, and this radius is 1 also. There are 3 triangles that we will draw based off of the unit circle where the lengths of the lines tell me how big trig functions are. So the first thing I want you to do is to draw some random triangle here in the first quadrant, any triangle. Here we see the radius is 1. These 2 other lines are trig ratios. This line is what I call the sine line. You can say it's opposite over hypotenuse, but because the hypotenuse is 1, the line's length will be the sine of whatever this angle theta happens to be. And then this line down here is the adjacent, but if you put adjacent over hypotenuse, well, that's going to be over 1, so this line is the cosine line. However long the line is, that length is the cosine ratio. So for instance, show several things real quick here. If I were to draw a 0-degree angle, this line is the cosine line, right, for a 0-degree angle. And so the cosine of 0 degrees equals 1. The vertical line is the sine line. So we know that the sine of 0 degrees equals 0, because there is no vertical line. If you were to go to a 30-degree angle, you'll notice if I were to kind of go right across here, this is exactly half. And so the sine of 30 degrees is 1/2. Now, we know this is the long leg, and it's pretty long. I mean, if this is 1, this is like, this would be half, this would be 3/4. It's bigger than 3/4. If it were a decimal, it'd be 0.866-ish. Or, in a radical form, it's the square root of 3 over 2. It's this half times the square root of 3. If I were to draw a 45-degree angle, this is a little bit bigger than half. In fact, it's almost 3/4. As a decimal, it'd be about, what would that be? About 0.707-ish. Well, that means that the sine of 45 degrees is the square root of 2 over 2. And the cosine line is going to be the exact same. It's also going to be the square root of 2 over 2. If you were to go to a 60-degree angle, you can now see that the sine or cosine line is half. Again, it's a visual thing. You can see the 1/2. So the cosine of 60 is a half. Well, remember when sine was half, this was square root of 3 over 2. This is half, that's square root of 3 over 2. The sine of 60 degrees, square root of 3 over 2. And then at 90 degrees, we can see there is no cosine line. That's because the cosine of 90 degrees is 0. The sine line is equal to the radius. The sine of 90 is 1. And again, the lengths of the lines are the progression. The main thing you need to memorize for now is that this line is the sine, this line is the cosine. You need to know which line's which. Does that make sense? You might also recall seeing this earlier in the year, that the sine squared theta plus cosine squared theta equals 1. You mean leg squared plus leg squared equals hypotenuse squared? Yeah, Pythagorean identity, but we can see it in the unit circle here. If we were to go bigger than 90, let's suppose we went to, say, 120 degrees. Well, here we have a 60-degree angle, don't we? So if I were to say, well, what's the sine and the cosine of 120 degrees? Well, this line sure looks like it's half, doesn't it? So I'll say the cosine line is a half, but notice it goes backwards. It's negative a half. And I just remember square root of 3 over 2 goes with the other one. Notice it's positive, it's upward, and it's pretty long, right? It's almost the same length. Well, what's the square root of 4, class? 2. So what's the square root of 3? Almost 2, right? What's 2 divided by 2? 1. What's almost 2 divided by 2? Almost 1. Square root of 3 over 2. It's an easy number to remember, especially since we've seen it so much already. If we were to go to the 45-degree angle, or the 135, I should say, with the 45 reference, we're going a little smaller, right? Square root of 2 over 2 for both of them. And we can see that they're the same length. We can also see cosine's negative, sine's positive. If we go a little bit bigger on the angle, now the sine looks like it's a half. Positive, by the way. That makes this the square root of 3 over 2. And we're going to go all the way to 180. Sine line's nothing, cosine's backward 1. And you can see these different lengths. I'll say this, the quadrantals are the real winners, because let's face it, the 0, 90, 90 triangle is the obnoxious one, isn't it? Okay? I don't need a 0, 90, 90 triangle, because I can see 1 for sine, 0 for cosine. 1 for cosine, 0 for sine. Negative 1 for cosine, 0 for sine. I can see them. And again, I don't even need to draw the picture. I can see it in my head. I can picture the circle, I can picture the line, 0, 1, right? Or 1, 0, right? I can picture those things. So that's where it's powerful. Notice down here, there's my negative half, negative square root of 3 over 2. Negative square root of 2 over 2, negative square root of 2 over 2. Negative half, negative square root of 3 over 2. Negative 1 for the sine, 0 for the cosine. And you can see all of these. I don't need those triangles for sine and cosine anymore. I can figure them all out from here. Go a little bit bigger. There's half for the cosine, negative square root of 3 over 2. Positive square root of 2 over 2 for the cosine, negative square root of 2 over 2 for the sine. Negative half, excuse me, for the sine. Positive square root of 3 over 2 for the cosine. And of course, we're back here to 0 again. And I can visualize all of it. Okay? Can you, or will you as we continue working on it? All right, so that's the sine and the cosine all the way around. Let's go to the next trig function, since we have 6 of them, right? So we need more than just sine and cosine, though that's, frankly, these are the 2 most common. These are the ones we use the most. Let's go to the next set of ratios. And you remember tangent is a term you learned in geometry? Remember, tangent's a line that touches a circle at only one point. Draw this on your paper if you would, please. And I want you to draw a line that is just tangent to the circle right at the end of the x-axis. This line is the tangent of theta. The line that's tangent is called the tangent. This line, now again, it doesn't actually touch at 2 points. It touches once. It would touch at a second point later. This line is the secant of theta. So you need to memorize that. Now notice sine and tangent are parallel. The difference is sine goes inside, tangent goes outside. Do we see that? And here, the radius is 1. So let's take a look, Chris, while you go back to the back of the room, and please, instead of in front, because that gets you right in front of the camera. No. Chris. Okay, so when you're sitting in this seat, if you have to stand up, if you go this way, you don't get in front of the camera. When you go this way, it juts you in front of the camera. That's why I say go to the back. Whatever, you're over there anyway. So we have the tangent, we have the secant. Okay, so let's see how this looks graphically here. That's a horrible circle. Well, if we have a 0-degree angle, there's no tangent line. That's because the tangent of 0 is 0. What about the secant? You go up along the tangent, right? And you go back down for the secant. So I go up for the tangent, nothing, and down for the secant. Well, the secant's the same as the radius. That's because the secant of 0 is 1. Let's suppose we went up 30 degrees. Now, this is one that you can't picture probably. You're going to have to memorize this one. The sine line would be right here. The sine is a half. This is the tiniest bit bigger than a half. A tiny bit bigger than a half is the square root of 3 over 3. That's not a number that's just, oh yeah, I can picture that right off. That's the one number I have to memorize, but it's the only one I have to memorize, is the square root of 3 over 3. No questions right now. The secant, of course, is going to be double the short leg, right? So the secant of 30 is going to be 2 times the square root of 3 over 3. Now, here's where it gets nice, is when you go to 45 degrees, what's true about these two lines? They're equal. Of course they're perpendicular. They're equal, right? Because it's 45 degrees. It's a 45, 45, 90. So since the radius is 1, how big is the tangent line? 1. The tangent of 45 is 1. And the secant, if it's 1 and 1, it's 1, 1, square root of 2. The secant of 45 degrees is the square root of 2. What if we had a 60-degree angle? Well, now we're clearly bigger than 1. In fact, if it's a 60, we've got 1, square root of 3, 2. And in fact, you can see the 2. So we know that the secant of 60 is 2. And here's our square root of 3. 1, square root of 3, 2. The tangent of 60 is square root of 3. Here it's big, square root of 3. Here it's really little, square root of 3 over 3. That's kind of how I remember them together. And then here's the great part. What if you went to a 90-degree angle? Tangent never stops, does it? Tangent is undefined, as is the secant, undefined. Both of them, because you can't finish a triangle. Both the secant line and the tangent line, they never meet up, correct? So at 90, both the tangent of 90 and the secant of 90 are undefined. But you can visualize all of it. Again, the only one I really struggle with is that square root of 3 over 3. I just have to memorize it's a little bit bigger than a half and it's outside, okay? But everything else I can visualize. Now, what if you come over here to this quadrant? 1, square root of 3, 2. Tangent square root of 3, secant's 2. Well, both negative in the second quadrant. This is where it falls apart. These signs, the SIGNs, work for sine and cosine. Up is positive, down is negative. Back is negative, forward positive, right? For the tangent and secant, outside quadrant 1, so quadrants 2 through 4, you're going to have to use ASTC. So jot that in your notes. You can't go on the direction of the lines. It just doesn't work. For instance, in the third quadrant, the tangent line is going to go down, right? Well, that doesn't mean it's negative. So in quadrants 2 through 4, you would have to use ASTC. But largely everything we do is based on reference angles anyway, right? We see some nutty angle, we get the reference angle, boom, there it is on the unit circle in the first quadrant anyway. So again, this allows us to visualize those. The last triangle deals with the last two trig ratios, which are cotangent and cosecant. Now, co means what?
Cofunction. No, complementary.
Complementary, good. Complementary means 90-degree difference. Notice how the tangent comes up and the secant comes down. The cotangent is going to be 90 degrees difference. It's going to go out and then come down with the cosecant. So draw another circle, draw another Cartesian plane inside, draw some line going out, draw some line coming back down. There's the cotangent of theta. Now notice where theta is though. This is theta still. Not in here. This is theta. Here's the cotangent, here's the cosecant, and of course the radius is always 1. Now the beautiful thing is, if you take the time to memorize the lengths of the tangent and secant together, the triangle is going to be the exact same. It's just going to come off the top. So making sure I've got enough room to the edge of the chalkboard here, let's take a look at the first quadrant angles. If I were to have a 0-degree angle, the cotangent line would go off to infinity, wouldn't it? So would the cosecant line. So at 0 degrees, the cotangent of 0 is undefined, and the cosecant of 0 is also undefined. Make sense? What if I went with a 30-degree angle? Well, you have to keep going until it hits here. Notice, well, this is maybe a little bit poorly drawn here, but if I have a 30-degree angle, notice it's 2 radii, right? The cosecant is 2 at 30 degrees. Remember, the radius is 1. If I've got 1 here, square root of 2 here, or 2 here, what's up here?
Square root of 3.
1, 2, square root of 3. The cotangent of 30 degrees is the square root of 3. What if I went with a 45 degree angle? Notice this is the same length as the radius. So what's the cotangent of 45? 1. And if it's 1 here, what's here? It's just a special triangle. The cosecant of 45 degrees is the square root of 2. Now, what if I went with a 60 degree angle? It's a little bigger than the half. What is the little bigger than the half I told you you're just going to have to memorize? Square root of 3 over 3. So the cotangent of 60 is the square root of 3 over 3. But if this is square root of 3 over 3, this is always double the short. So what would the cosecant of 60 degrees equal? 2 square root of 3 over 3. And what if I had a 90 degree angle? How big is the cotangent line?
0.
0. There's nothing there, right? The cotangent of 90 must be 0. How long is the cosecant line?
1.
It's the radius. It's 1. And like this, once you get out of the first quadrant, the sign conventions of up and backward and forward all break down. So here as well, quadrants 2 through 4, you're going to have to use ASTC. So then, let's take a look at all 6 trig functions in an instant with any given angle. Let's just start with 0 degrees. Let's suppose I have a 0 degree angle. That's what it would look like, correct? Now then, how big is the sine line in that picture, class? Remember, the sine is the vertical line. How big is the sine line here?
0.
0. So we know that the sine of 0 degrees is 0. How big is the cosine line? 1. Just 0 degrees. How big is the tangent line, class?
1.
0. How big is the secant line?
1.
How big is the cotangent line?
0. Undefined. 1.
It would keep going infinitely, wouldn't it? It's going to be undefined. Excuse me, cotangent of 0 would be undefined. What about the cosecant line that goes with it? Also undefined. I didn't have to think of any ratios at all. In fact, technically, once you've done this a few times, you don't even have to draw the circle. You picture this in your brain like, all right, so I guess turning from your perspective, 0 degrees, sine 0, tangent 0, cosine's 1, secant's 1, cotangent, cosecant are both undefined. And you do it all in your head, mentally picturing it. Let's go to the 30 degree angle. And let's get all the trig ratios. I can draw it semi-accurately. How big is the sine?
Square root 1/2.
Half. How big is the cosine?
Square root 3.
Almost 1.
So square root.
Square root of 3 over 2. Right? Square root of 4 over 2, that'd be 2 over 2, which would be 1. So it's just a little less than square root of 4 over 2, it's square root of 3 over 2. How big, if I extend it out just the tiniest bit, how big is the tangent line? It's just a little bigger than a half.
Square root 3 over 3.
Square root of 3 over 3. How big is the secant line?
Square root of 3.
Double it, right? This is short, so double it. 2 square root of 3 over 3 is the secant. What about if I go all the way out to the cotangent? How big is the cosecant line?
2.
2. So how big is the cotangent line?
2.
Nope.
1/2.
It can't be the same as the hypotenuse. This is 1, this is 2. What's that one? 30, 60, 90.
Square root of 3.
Yeah, square root of 3. 1, square root of 3, 2. And you get all 6 trig functions at a 30 degree angle quickly just off of line diagrams. Let's do 45. I can go right down the middle. Now here, it's not almost 1, but it's also not a half. It's in between. How big is the sine?
Square root of 3.
No, square root of 3 over 3 would be out here. It's a little bigger than that, but not by much. Square root of 2 over 2, right?
Oh.
Square root of 1 over 2 is a half, right? So square root of 1 over 2 is a half. Square root of 3 over 2 is almost 1. It's right in between, which would be square root of 2 over 2. So the sine is square root of 2 over 2. What about cosine? They're the exact same. Yeah, square root of 2 over 2. What about the tangent?
Undefined.
It's the same length as the
One,
radius.
one.
You should be able to see it as the radius is 1, right? And of course this radius down here is 1. What's the secant then? If it's 1, 1,
2.
45, 45, 90, 1, 1,
Square root of 2.
square root of 2. What about the cotangent line? 1. What about the cosecant line? Square root of 2. Right? It shares the secant line. Okay, so again, you still have to this is assuming you know the triangles over there already very well, then you can base it off of that. But yeah, I'm starting to get the hang of it. All right, let's go to a 60-degree angle. Let me not go to a 60, just kidding. Let's go with this piece of chocolate. Let's try a 60-degree angle with this one. Notice the cosine line first of all. Half. So how about this line, which is almost 1?
Square root of 3.
Now here, the tangent line is like this, but notice first of all the secant line. Double, so 2. What about the tangent line then? We got 2 here, 1 here,
Square root of 3.
square root of 3. Notice it's big, but not quite double, right? Because it can't be. All right, what about the cotangent? Notice here's half. It's a little bigger than half.
Square root of 3.
Square root of 3 over 3 is that little bigger than the half. And then this was going to be double that, remember? So the cosecant,
2 times square root of
2 square root of 3 over 3. Let's go to 90 degrees.
Is 90 the easiest one? In your
0 and 90 degree are the easiest. All right, so we go with a 90-degree angle. All right, so there's the rotation. How big is the sine line? 1. How big is the cosine?
0.
0. How big is the tangent?
1 to 5.
How about the secant?
1 to 5.
How big is the cotangent?
0.
How about the cosecant?
1.
Boom. Do you see it? If nothing else, the quadrantals, so much easier with the unit circle. Again, as you start to kind of memorize the pattern, okay, half and square root of 3 over 2 go together. Square root of 2 over 2 and square root of 2 over 2 go together. Square root of 3 over 3, 2 square root of 3 over 3 go together. Right? And you kind of memorize those patterns. This will become a lot easier for you. Questions on this? All right, yes. Again, is this absolutely necessary? No, but it could really speed up your work. I've had students who never get it. In fact, most of my students, frankly, don't get it, okay? That's okay. Historically, I try to explain it the best way I can. If you can get it, great. I've had a few got it, man, are they quick. And I've got some, not so much, not so much. Okay, questions?
The square root of 3 over 3, wouldn't the
It's like
square-
0.6-ish if you put it on a
I was gonna say,
decimal.
wouldn't square root of 3 be half? So it would be 1 over 2.
No, it's not a half. Square root of 3 is like 1.73, blah, blah, blah. You divide that by 3, it's about 0.59, blah, blah, blah. So a little bigger than half. All right, your homework this evening is to read pages 70 to 72, reviewing over some stuff that we talked about in Algebra 2 with function notation. So read pages 70 to 72, and then do ACT Set 5. ACT Set 5, questions 49 to 60. All right, have a wonderful rest of your day, and you are dismissed.